I'm going to go through and give you some of the notes that I gave in class on Monday, November 29th. I want to kind of talk about them as you write them down. I think it's going to be important, so hopefully this will work pretty well. Should have put a hard copy in your mailbox. So how are nuclear reactions similar to chemical reactions? And I started off the day's discussion with asking, do you think we should be using nuclear materials? And a couple of my classes gave some pretty thoughtful answers, but we might not know what those nuclear materials might be. Some people thought about bombs and weapons. Other people thought about things like nuclear power. So that's kind of led off the discussion. So in this particular case, nuclear reactions and chemical reactions are similar in that these both occur on an atomic scale. In other words, in atoms. Differences here why did that do that? I do not like that it did that. Oh well, we'll see. I'm just going to have to go with it. Differences here are that nuclear reactions occur in the nucleus of atoms, while chemical reactions involve the valence electrons, which are in the electron cloud. The other difference is that in chemical reaction, the elements in the reaction don't change. So if you start with hydrogen, you have some hydrogen at the end. If you start with carbon, you end up with some carbon at the end. Now they could be rearranged into different formulas and compounds, but the elements don't change. In nuclear reactions, new elements can be created. So if you didn't have something like carbon at the beginning of the reaction, you could have it at the end. A transmutation is basically when one chemical element or isotope is converted to another element due to the number of protons or neutrons if it's an isotope being changed. So the number of protons defines the element itself. So if we change the number of protons, we're going to change that element from something like, again, carbon to maybe nitrogen. Two ways that transmutations can occur. First of is radioactive decay. This is when an unstable nucleus, usually a large nucleus or a nucleus with an unbalanced number of neutrons compared to protons, emits radiation by giving off daughter particles. So the beginning of the reaction, the product that we start with nuclear reactions are called parent particles. The particles that are given off are called daughter particles. You could also give off energy. Nuclear reactions are another way that transmutation can occur. This is when I want to make sure I make that blue. This is when an outside particle, and it could be something, often it's a neutron, and often it's humans who are basically separating neutrons and shooting them into these types of reactions. But that's when it reacts with the nucleus of an atom, and that would begin a nuclear reaction. In nature, we have a number of radioactive decays. Three of the most common are as follows: an alpha decay. So in an alpha decay, this is when a parent nucleus gives off an alpha particle, and that's basically helium with 2 protons and 2 neutrons. This is the least energetic and least penetrating, meaning it can't penetrate your tissue very well. Type of decay. And I've got an example down here. So essentially with nuclear reactions, you have to have the same mass number on the left as you have the total on the right, and the same proton number on the left as you have on the right. If you recall from when we've written atoms before, we have something where we have the mass on top and the atomic numbers on the bottom. So if I've got 235 on the left-hand side here, and this alpha particle has a mass of 4, that means my other particle needs to have a mass of 231. So 231 is equal to 235 equals 231 plus 4. The atomic number down here is 92, and if helium has 2, then thorium would have 90. So 92 equals 90 plus 2. I'm going to finish off today with beta decay and gamma decay. So beta decay, it has a middle amount of energy. And this type of decay happens when a neutron splits apart into a proton, and that stays in the nucleus. And an electron which is given off. The electron is known as the beta particle. So an example is down here. Once again, the total mass number at the beginning is 235. The total proton number is 92. So if you give off an electron, we're going to call that a -1 proton number to help this work out mathematically. The mass is essentially 0. And so we've got 235 on the left, 0 mass. So the new daughter particle is going to have 235 mass. But since we have -1 here for the electron, this actually goes up in number. So we have an additional proton, and that changes the element from uranium to neptunium. And you'd have to use a periodic table to look for that. The final one down here is gamma decay. And gamma decay is when you have a high energy parent nucleus gives off a high energy photon with no protons and no mass. So essentially what happens there is you're only giving off energy, and the particle at the end is the element at the end is the same as the element at the beginning. This little Y symbol is the gamma particle. So you might have heard of gamma rays before. That's exactly what's going on. This goes through a little bit about how to perform the reactions mathematically and what's happening. So that's kind of a physical representation. What I'm asking students to do in class is to complete these 5A through F with the reactions, and they're listed as alpha, beta, or gamma and then we have not yet done this in class. The periodic table on the back has all the elements. It's a little longer than the one I gave you, and we need that for some of the reactions here. So you're going to want to look at the atomic number and the atomic mass, and those are given here. Okay, so hopefully that helps.